right, welcome back, class. So we're now going to move into the kind of final topic of discussion for this course. In the past few months, we've really built from scratch a theory for how molecules fluctuate and how those fluctuations give us insight and predictive ability to what we observe on actual macroscopic scales. However, that discussion has been very much limited to properties of materials and systems which are static, which are thermodynamic in origin. We have means to compute or measure or predict the heat capacity of a material by understanding how its energy fluctuates. We have an understanding of why spontaneous processes occur. However, what we have not said much about at all is how fast they occur, or why does it take so long for a particular process to occur spontaneously? What sets the timescales for the motions of atoms and molecules? So that's what we're going to focus on in these last 2 weeks. Really questions of dynamics, how fast molecules move, why are some things comparably slow? So to have that conversation, we need to start by orienting ourselves to the kinds of scales, time scales, that molecules care about, much in the same way that in the very beginning of the semester, we had to orient ourselves to the energy and length scales that molecules care about. So a way to think about this question is to ask kind of what is the typical speed of a molecule, or over what sorts of time scales do molecules explore space or configurations? What is the walking speed of a molecule, if you will? So let's think. So there's a couple different characteristic molecular motions that a small molecule might undergo. It might vibrate. It might rotate, or it might translate. And you can imagine that those different processes have different associated timescales. If we were thinking about a vibration, one might ask specifically, what is a characteristic timescale for one period of an oscillation in a typical covalent bond? Those timescales on our units, on macroscopic units, are incredibly small. A characteristic period of vibration is 10 to the minus 14 seconds. Put in a unit that molecules care about, that is 10 femtoseconds. That's a typical period of, say, an OH stretch. Analogously, if we were to thinking about rotations, well, rotations you can imagine have slightly longer characteristic timescales. Rotation of some larger molecule is going to be slower than the very fast oscillations. We know that because, for example, we know that the characteristic energy scales for rotations are much smaller than for vibrations. Correspondingly, a typical rotational timescale, say a period of one rotation, is something like 10 to the minus 12 seconds, or about a picosecond. Say, for some simple diatomic, where instead of stretching, it's undergoing some simple rotational motion. Now, translational motion, to talk about a characteristic timescale for translational motion, we have to set the length scale over which we're talking, right? While a period of a vibration or a period of rotation has in it kind of a built-in scale over which that motion is occurring, one period, translation is different. We have to set a characteristic scale over which we want to ask how long does that translational motion occur on. So if we set that scale, say, for example, for a molecule to move, say, its diameter. So that's a microscopic distance. Let's call that diameter d. Well, that characteristic timescale for that translational motion over its diameter would be that diameter. If we imagine the molecules are moving with constant speed over that length scale, then the time scale is just going to be the length over which it translates divided by some typical speed that it does so with. Now we know that a typical speed of a molecule, something we can compute in the units that you'll never forget, it's about 1 football field per second. In SI units, that's about 300 meters per second. If a typical diameter, say, of a small molecule is 3 angstroms, that boils down to or results in a typical timescale for that translational motion, which is about a picosecond. So in our little diatomic molecule that we've been thinking about, that's translating d, and it does so in 1 picosecond. So those are the kind of basic timescales, the basic units over which we should think about meaningful molecular motion. On timescales shorter than picoseconds or femtoseconds, molecules don't do anything. Now, the electrons in those molecules are actively moving, but the heavy atom motion is comparably minimal on timescales shorter than, say, about a picosecond. So that sets the scale. And on these sorts of scales, so compared to these scales, a reaction, say, that takes place in a characteristic time of a microsecond is essentially an eternity. If picoseconds are the characteristic timescales over which molecules move about their day, if a reaction happens only once every microsecond, well, the difference between microseconds and picoseconds is 1,000,000, factor of 10 to the 6. So if we think about seconds the way molecules think about picoseconds, well, what is 1,000,000 seconds? 1,000,000 seconds is something that is a pretty comparably long time. So we will denote these sorts of characteristic time scales, the scales that molecules care about, femtoseconds or picoseconds, as tau mole. That's the basic unit of time that molecules will undergo significant motion. So those are the fastest motions we'll care about. And the details of those motions, well, those are mostly mechanical in a simple way. We just worked out translational motion just by knowing Newton's laws and knowing what we mean by velocity. Rotational vibration, those are slightly more quantum mechanical. If we really wanted to understand the dynamics of those motions, we would solve Schrodinger's equation. What we're going to focus our attention on more is those dynamics which occur on comparably longer timescales, the slow dynamics that molecules can undergo. So what are some comparably slow motions? about that. Got zoomed in somehow. So, well, one obvious motion which occurs on a much longer time scale than what we've just considered would be to think about translations over distances much larger than molecular diameters. So let's ask the question in air, for example. How long would it take for a molecule to move 3 meters? So 3 meters, that's not so much larger than one of the smaller distances in the room that I'm in. So how long do I have to wait if I tag the molecule on one side of the room for it to move across the room? So we might expect that that characteristic timescale could be computed by knowing that same typical velocity and asking, in that typical velocity, how fast do I move? If I move 300 meters per second, well, then I would just divide 3 meters by 300 meters per second, resulting in something like 10 milliseconds. That turns out to be not at all the case. It takes significantly longer for a molecule on one side of the room to get to the other side of the room. In fact, to go 3 meters in air would take several days. That's a crazy long time. It's important to ask, why on earth would it take so long if the molecule moves so fast? Why would it take so long on average to get from one side of the room to the other? Does anyone have? You should think about this. Then take a second to. You might pause the recording and think, why? What could be happening that would slow that molecule down so much? Well, of course, that's because the molecule doesn't move ballistically across such a large space. It necessarily is going to run into things. In fact, even though the air is significantly dilute, so dilute that we can, for all intents and purposes, thermodynamically neglect interactions between gas molecules. That's why the ideal gas law works so well. Dynamically, we can't ignore those collisions. In fact, if you were to spray some cologne over on one side of the room very carefully, such that you didn't create currents and convective flows, and allow just molecules to diffuse from one side of the room to the other, it would take a very, very long time, because those molecules bump into each other, randomizing that motion, moving both forwards and backwards. Similarly, if one was to think about in a liquid, how long would it take for a molecule, say a tagged H2O molecule, say to move 3 meters in a pool? So again, while on very short length scales, that water molecule will move with a constant speed, in a liquid, there are many molecules surrounding that given tagged molecule. So there are many things that it's going to run into, randomizing that motion. It's going to take a comparably longer time, one might expect, in a liquid, because there are so many additional sources of collisions. If you allow for only diffusive motion, not injecting any additional energy into the system, just allowing it to explore its thermodynamic state, a molecule in a liquid to move 3 meters would take about 100 years. That is an obscene amount of time. It's much antithetical to our intuition. We don't think of things taking that long, and that's really because usually when we experience these sorts of motions, we are adding in significant amounts of additional energy. However, if you were to actually pull up a video, say on YouTube, of an ink drop very delicately placed at the top of a glass of water or at the bottom of a glass of water and allow only diffusion to take those molecules and mix them, it would take hours and hours for that diffusion to happen. So that is to say that translation over large scales is a comparably slow process because ballistic motion doesn't last very long. Molecules inevitably collide, randomizing directions. And greatly reducing mobility. Those sorts of diffusional processes are something we'll focus on next week when we talk about diffusion and develop a model for those collisions and how the molecules eventually do emerge and translate over long timescales in spite of those collisions. But what I want to start with today instead is another comparably long timescale event, or a slow molecular motion that's a little more near and dear to our hearts, which are chemical reactions. So an example of a chemical reaction and its associated time would be to ask, for example, how long does it take for a given tagged water molecule to dissociate? So we know that if I was to grab a water molecule in a glass of water, there is some chance that that water molecule will fall apart into a H plus and an OH minus, the basic process which generates pH in solution. Does anyone have any idea for how long that takes on average? If I was to track a water molecule as it moved about a liquid, how long would I have to wait to see that tagged molecule undergo autoionization? It's much longer than I would have naively expected before I knew this number. Turns out that the characteristic timescale for that reaction, autoionization, is about 10 hours. So again, on the timescales that molecules care about, this is an incredibly long time. That is, 10 hours. Well, 10 hours, there's a 60 seconds in an hour, and 60 seconds in a minute, and 60 minutes in an hour. That gives us 3 orders of magnitude, 4 orders of magnitude when I go to 10 hours. So that's 10 to the 4 seconds. Molecules care about picoseconds, which is 10 to the minus 12. So that's 10 to the 16 times larger than the kinds of scales that molecules care about. Why is it that such a process is so slow? Unlike diffusive motion, which we just talked about, the molecule doesn't have to move over long distances to autoionize. It just needs to go molecular sorts of distances to break one of those OH bonds, adding a proton, say, to some neighboring water molecule. So it's not that there's a great distance to overcome, and it's not that moving about that distance or over that distance is fundamentally slow. It doesn't take a molecule, doesn't take that proton 10 hours to move onto an adjacent water molecule. Rather, what is slow, or why it's slow, is that the reaction must proceed through a very improbable state. A very improbable fluctuation must occur in order to have that reaction happen. Let's take as a concrete example the isomerization of methyl isocyanide to acetonitrile. So methyl isocyanide, I am told, has the conductivity of a methyl group attached to a CN group, or an N bonded to the N of a CN group. So this is methyl isocyanide. It can isomerize, forming acetonitrile, where that methyl group is now attached to the carbon. And that is a reaction that if you go and Google characteristic rate constants for such process, it happens about once per millisecond. So again, that's a rotation of that CN group about some bond. So it's not that that basic rotational motion is slow, that's going to occur on a picosecond, but rather to have that motion occur must have required a pretty rare fluctuation. If we were going to try to sketch this process out, we'd have our little methyl group over here, attached initially to CN group. We imagine rotating about some axis, intermediate to forming the actual acetonitrile. We will go through a state which looks very strained, which looks energetically very unfavorable, where I've broken that bond between the methyl group, the carbon on the methyl group, and the nitrogen in the CN group. So that very strained configuration has a, we should expect, would have a very high energy. And we know, with the tools of statistical mechanics now under our belt, that a very high energy state is one which occurs with very low probability. So therefore, there's some simple reasoning that lets us understand why such a process would be slow. It's not that that rotational motion is fundamentally slow. It's just that to access that reaction, to actually go between the reactants and the eventual products, requires a fluctuation which is so rare that the likelihood of seeing that fluctuation in any given time is so low that I have to wait for many attempts of that process for me to actually see that reaction take place. We'll denote such states, such high energy, low probability states that reactions have to pass through in order to transfer reactants to products as transition states. And we'll give them this kind of characteristic double dagger notation. So again, requires a very rare fluctuation, a very rare concentration of thermal energy that allows that molecule to overcome a very low energy state, a very high energy state, a very low probability state for that reaction to proceed. Once that fluctuation has occurred, the reaction is going to proceed very quickly. That rotational motion is fast. It's just that you have to wait long enough to see that improbable fluctuation. So in order to make this a little more quantitative and concrete, we need to introduce the means in which we characterize reactions, and that's with so-called rate laws. And here at the beginning, we're going to focus on simple so-called unimolecular reactions. Unimolecular because they take one atom or molecule and with some rate, call it K, transfers that atom or molecule into some new product state. An example might be that isocyanide to acetonitrile isomerization, or might be a ring opening like that. Those are reactions that don't require two molecules to meet each other to then react, which would then couple slow diffusive motion with these improbable fluctuations. Such bimolecular reactions we'll consider in a few days. But to start with, we'll think about just simple unimolecular reactions. An important concept in these sorts of systems is the idea of a correlation time. If we're going to characterize reactive dynamics, we have to have some basic language to think about events dynamically. And a correlation time is one such mechanism that lets us do that. A correlation time is essentially a measure for how long a molecule remembers what it was doing. So consider, for example, some diatomic undergoing some vibrational motion in solution. We can measure that vibrational motion by monitoring that bond distance, call it R. Now, there is some typical bond distance, some average value that over long times, if the system is undisturbed, it will fluctuate around. We know how to quantify the characteristic sizes of those fluctuations. What we need to build some tools to do is understand how those fluctuations might actually occur in time. So if this is actually fluctuating in if this was fluctuating in dissolution, what we might imagine for a typical time series of this bond, well, maybe it looks harmonic initially. That would be perfect harmonic oscillator behavior. But if it's in solution, every once in a while, there's going to be a collision with a solvent molecule that changes that period of oscillation. So for example, here might be examples where a solvent collided into that diatomic, changing that period of oscillation, or one might say, decorrelating it from its initial harmonic motion. The period after a couple collisions that diatomic molecule is now undergoing is not in sync with the period it was undergoing initially. If I wanted to measure or define a measure of that correlation in the oscillations of that diatomic molecule, I might average over many of these time series, over many realizations of this motion, many realizations of collisions with surrounding solvent molecules. And if I was going to then plot an average time series, given that I start with some value, say R naught, as a function of time, well, that conditioning implies that I start at that specific value at time 0, but the fact that those collisions cause me to fall out of sync, out of phase with the oscillations in that vibrational motion means that on average, what I would see is that this function, that average, would decay. At long times, it would forget that it started at R naught, undergoing random collisions with the solvent, coming out of phase with that initial periodic motion. And we would say that the characteristic decay time for losing that memory, forgetting that I started at R naught, that timescale is what we mean by a correlation time. And typical correlation times for most processes are not that much longer than tau mole, the typical timescales of those basic motions themselves. So how can we use this accounting, this measurement of a molecule forgetting what it's doing to help us understand and quantify what we mean by the rates of chemical reactions? So for a chemical reaction, let's imagine gridding up time into little segments. We'll denote the length of those segments, delta t, and we'll choose delta t to be much longer than tau mole, and therefore much longer than typical correlation times, but much smaller than typical reactive times. So they're reactions occurring on much, much longer timescales than typical molecular motions means that there's a wide separation of timescales between a molecule forgetting what it's doing and it eventually undergoing a reaction. And in that limit, if we grid up time in such a way, what that means is that in each interval, it represents a statistically independent attempt to react. So each interval by construction is statistically independent, and therefore I can ask in a meaningful way in one of those intervals if the molecule has reacted or not. And because those are independent, then each one of those segments represents an independent attempt or an independent time over which that molecule could have reacted. We can quantify that by defining P sub delta T to be the probability that a reaction occurred in one of those intervals. And we expect that if a reaction is really rare, that P delta T is something much, much smaller than 1. And therefore, to first order, proportional in the length of that interval, so proportional to delta T. If we define a rate, K, well, a sensible way to think about a rate then is that probability that that reaction happened per that unit of time, delta T. So that's really what we mean by a reaction rate constant. The rate at which a reaction happens is just the answer to the question of, in some small unit of time, did that reaction happen? Probabilistically speaking, then one would say that the rate is the probability that that reaction happened in some finite interval of time, delta T. And therefore, roughly how long we have to wait for a reaction if we call that characteristic time tau reaction, it's going to be roughly delta T times the number of intervals we have to wait before a reaction occurs. And if every point in time is equally likely of having that reaction, then the number of intervals we have to wait on average should just be 1 over P delta T, which is then just 1 over that reactive rate constant. So if I wanted to, say, ask how many coins do I have to flip in order to see a head, well, a naive expectation would be to say 2. If a head is one has the probability if I flip a coin and get ahead occurs with probability 1/2. Then 1 over that probability tells me the expected number of events I need to observe before I'm very likely to have seen that event happen. Similarly here, if p delta t is the probability that a reaction happened in some delta t time, 1 over that tells me how many of those time intervals I needed to have waited in order to see that event. Now we can do this a little more carefully by asking a more specific statistical question, which is, what is the probability that a reaction still hasn't happened after n intervals? Well, the probability that it hasn't happened in one interval is just 1 minus the probability that it happened in that interval. If p delta t is the probability it happened, 1 minus it is the probability it did not happen. If all of those segments, all of those delta t intervals are statistically independent, then the probability that it didn't happen in n of those intervals is just 1 minus p to the n. Now that's something we can rewrite through understanding the mathematics of exponentials and logs as e to the n log 1 minus p delta t. Again, if I take the log of something raised to a power, I can pull that power out in front of the log. That's where the n comes from. E to the log is just the argument of the log. And the limit that p is small, the probability in a given interval is small, well, then I could expand that log. 1 minus a small number to first order is just that small number. So I have e to the n p delta t if p is small. If I multiply and divide the argument of that exponential by delta t, I have n delta t's times p delta t over delta t. In delta t's, that's how long I've waited for that reactive event to still not have occurred. So that is the time. P delta t over delta t, that's what we meant by our reactive rate constant. So what we've just found is that the probability that a reaction hasn't happened in some interval, if those intervals are statistically independent, is just the exponential of the waiting time t times that rate constant. So it's an exponentially decaying probability whose rate is determined by that reactive rate constant. So initially, if we have, say, in a 0 reactance, the average number left after some time let's denote that average with a bar. So after a time t, if I started with in a reactance, the average number that are left is just the number that I started with times the probability that any one of those have reacted, which we've just worked out is e to the minus kt. If I divide by v on both sides, then I have the concentration of A at some time t is the concentration I had at the beginning times that decaying exponential function. If I took the derivative on both sides, I have that the concentration changes with time at a rate, k, times that concentration. That is just the equation for first order kinetics. That's a first order rate law. The change in the concentration of some set of reactants A is equal to minus the rate that they change, that they react, times that concentration. So that's something you have undoubtedly seen all the way back in your introductory physical chemistry classes. You were told that first order kinetics have this specific form. What we've seen now is that this macroscopic observable of first order kinetics is the result of very specific microscopic dynamics. The fact that a rate is a rare event, that such that if I look at any specific interval in time, that the likelihood that I react is small in those specific intervals, and that if those intervals are uncorrelated, we will naturally get an exponential decay of probability that I react. Put in terms of concentrations, then that statement is just that the initial set of reactants concentrations decay exponentially, or that differentially speaking, the rate of change of those concentrations of reactants is equal to that rate constant times how many reactants there are. So we have an understanding now of where first order kinetics comes from, and really what we mean by a rate constant, by a reaction rate constant, this K, that is really, statistically speaking, the probability per time that a reaction occurs. So where that leaves us then is to the question of, can we, from molecular principles, calculate K? K is the probability per time that a reaction happens. And we've just, at the beginning of this lecture, discussed, well, most chemical reactions are slow because they have to access improbable states. But we know the likelihoods over which any state in equilibrium is sampled, is observed. That's given by Boltzmann statistics. So it should be intuitively true that we should have something to say about that reactive rate constant just by knowing how likely it is to see, say, transition states relative to just reactants or products. A simple calculation that we will do next time, that I'll introduce in the last few minutes of lecture, which will help drive this specific point home, is the calculation, or is the understanding of so-called effusion. Effusion is the process by which I set up some concentration in one region, call it A. Let's imagine that that region is just some cube of length L cubed. And if I was to poke a little hole in that volume and connect through a small opening that tube to another volume, say region B, of similar size, Effusion is the process by which particles that start in A eventually make their way through that small opening into B. If we drew a coordinate system, say, call this direction here X, that length is L. Let's call this length XB, and therefore this XB plus L. So if we were to say have a gas over in region A, if it was going to make its way into region B, molecularly, what must happen is there must be a fluctuation in that gas molecule that goes and finds, after moving around in that space, that little opening that's going to connect it into region B. So let's imagine, for concreteness, that this thin tube that connects these two regions has a cross section A, which is much, much less than L cubed, such that it really is a very small hole in a big box. That tells you that this event, the rate at which an A goes from B, occurs through a rare fluctuation by which it finds that little opening. So it would be reasonable to say that what needs to happen is that molecule reaches some transition state in that it finds a hole or means by which it can go through that tube. We will be able to very concretely address the question of how quickly do molecules escape from A to B. By understanding the probabilities that that gas finds its way into that small opening. And so it should not surprise you that the escape rate is roughly going to equal the number of molecules at that transition state times then just the typical drift across that transition state, the typical flux or velocity across that region X dagger. And so that will be kind of our first toy problem to understand how we can estimate rates of rare events. Here is the rate of which a gas escapes one container and moves into the other container, what we mean by effusion. But the lessons that we'll learn in doing that calculation will help us generally understand rates of rare events occurring through much more complicated molecular reorganizations. All right, so stay tuned for that. We'll continue this discussion next time.